Hello and welcome everybody for the DevFest 2019. Technically, it's 2022. Uh, so after 2019, this is the DevFest we have organized um, for the Google community all over the UK and Ireland. We have a set of talks and workshops, but this virtual show will be focused on this particular will be AI and ML. We have with us, we have Santosh and Mittal, who will be talking about um, how we can accelerate data journey on Google Cloud Platform with automation. And there are two uh, speakers for this talk: Santosh, which works on who works in apps broker with 13 years of experience in software development, and recently he's been working in data science for last 4 years. He's ML engineer. He will be discussing this topic with Manish Mittal. I'm bringing on both of them so we can have a discussion so they can later on start the conversation. Hi Manish. Hi Santosh.
Hi, everyone.
Santosh, you are mute.
Hi everyone. Hello Yasser. Thanks for introductions.
So can you tell us what you are going to talk about today in general?
Sure. Yes. So we'll be talking about how we can accelerate a data journey using the Google Cloud Platform, and what are the main challenges we face, and how these accelerators are going to solve those challenges. That's at a nutshell. So if I can start off with the presentation, sharing my screen. Yes, sir.
Yeah, we let's. You can put the presentation on. We'll start it at 10:30 because we have the schedule. People will join at that time. You can put on the presentation. That's fine. And please also tell us about yourself.
Yeah.
I can introduce to a limited data. You can introduce yourself well, and Manish as well.
Yeah.
Sure. So I am Santosh, work for Apps Broker. So I've got 13 years of development experience, of which 4 to 5 years is into developing ML engineering workloads for Lloyd's, Apps Broker, and other clients, etc. That's my professional life. Academically, I have my master's in data science and machine learning, and from University of Edinburgh, and I'm currently pursuing my PhD, studying about how the explainability of deep learning works in
All
the
right.
commercial space. That's
And
about.
what about Manish?
Yeah. So, hi, everyone. I'm Manish Mittal. I'm solution lead at Apps Broker. So, my role at Apps Broker is of pre-sales, and part of my role is also of delivery focus, which is acting as a principal data engineer and MLOps architect. I have more than 13 years of experience in data analytics space, especially in AWS and GCP side of things.
Okay, so Santosh, go ahead and share the screen. I'll go off now. So I'll come back at after 25 minutes. So
Sure.
thank you. Bye bye.
So this is a topic we are going to talk about. So accelerating data journey using the Google Cloud Platform, and we leverage all the automation related engineering aspects to accelerate that journey. So let me begin with the agenda. So we'll be talking about a quick overview of what MLOps is and why it matters. To answer why it matters, we'll go through the challenges, ML engineering challenges we face, and the data engineering challenges in particular, and how the accelerators we have developed will address these challenges, and how we can attain the benefits. So that's the overall agenda. Moving on. So the first question: what exactly is MLOps? Um, let's put the definition in a very casual way, layman terms. So what is MLOps? MLOps is a discipline which establishes a framework, and it allows us to adopt best software engineering principles to the machine learning science. So we are bringing the engineering skill, all the engineering practices, and attach them to the science to make it more reusable and robust. That's all about MLOps and how we do that. So we'll use four key principles to adopt that strategy or a framework. So what is it? The first one is standardizing the processes. We'll standardize all the processes that run around machine learning workload, like data ingestion to the staging models from developments to production environment. So all that processes are standardized. Second, we should have the ability on the platform where we can automate lifecycle management of various artifacts. Those artifacts can be your models, can your data, training data, evaluation metrics, etc. So they are stored, versioned, audited, and logged at scale. And the two main important aspects of the platform should be reusability and reproducibility. And why these matter? Because of the inherent non-deterministic nature of machine learning algorithms, how they run, on what systems they run, at what time they run. So there are some inherent non-deterministic processes that happen within that algorithms. So what we do is we ensure that it is reproducible and of course reusable. And the most important thing, the key thing is the platform itself should be democratized in the organization. So we should have various teams easily integrate, plug and play with the platform. That's the main aspect. And that's when all of the system, all of the platform will be highly reusable, customizable, and very generalized architecture. So that's what should be an ideal MLOps system should look like. Okay, why it all matters? So it all matters because we want to solve the challenges we face in ML engineering. So if I talk about the challenges we face in ML engineering, two kinds: conceptual challenges and then the operational challenges. I'm not boring you to death running through all the conceptual challenges we have got. At a very high level, the conceptual challenges arise because all the machine learning workload is predominantly driven by the inherent data dependencies, and that causes a depreciation in the models. The technical term is concept drift. So that is a main problem, and that changes the um, overall principles of the engineering aspect when it comes to ML science. So that's the main problem. And of course, with the lack of standardizing all the systems that run around the machine learning, and the quality of the data, expectations, data sufficiency to run the algorithms and get and do the inferences, these are all the conceptual challenges. Of course, we'll try to solve these conceptual challenges with the frameworks we have discussed earlier in the slide one. But that brings us with other set of operational challenges. Now these operational challenges are the challenges we face during the implementation phase. So what happens is the normal software engineering principles will slightly differ when it comes to machine learning, and the crowd itself who produce machine learning artifacts, data scientists, they might not be quite close to the usual software engineering principles, and that friction will cause these operational challenges. So for example, if I quote an example, so reusability, that's a change to bring into the way researchers or data scientists work, and change is always difficult. So how we adopt to that? The next one is apply the standard software principles like versioning, rolling back, do a canary deployment, making sure our deployments will not cause outages. So all of that should be applied to ML engineering. Again, that's a massive change that should happen to how the models are handled by data scientists. And whatever the new architecture that comes in to handle this. So far we know that the scaffolding for machine learning models is different from the scaffolding we build for the usual app dev. Now, so this new scaffolding should be in line with the organizational standards. That's a massive change. So that's another change we have to bring in. So if you see here, these are all the operational changes that we have to face and solve, which takes time, commitment. And other major problem is, or the other major challenge area is data itself. So the machine learning model or the engineering or the pipelines or artifacts, anything of that related to machine learning can be only as good as data that is powering it. And that's where comes the challenges we are facing in data engineering. So at this point, I'll hand over to my colleague Manish, who will talk about that in detail.
Sure, thanks, Santosh. So before going on to discussing with data engineering challenges, let's talk about what data engineers do and what is data engineering. So data engineers set up and operate organizations' data infrastructure, preparing it for further analysis by data analysts and data scientists. Then data engineering is a set of operation aimed at creating these interfaces and mechanism for the flow of information. And it can be a data lake, it can be a data warehouse, or any data pipeline. So in today's world, modern data engineering market is shifting very quickly to modern cloud-based data platforms. So let us look at some of the common challenges faced by data engineers and data architects. If you see right-hand side, there is a survey report which I pulled from State of Data Engineering 2020 report. If you see, this is the mean score basically. The more closer to 5, that means the challenge is extremely critical, and the more it narrows down towards 0, the challenge is less critical. So if you look at some of the top challenges, it talks about data quality validation, monitoring and auditing in cloud. Then it talks about anonymizing of personal identifiable information. Then what I have done is I have broadly classified these some of the top challenges which are identified by data engineers and data architects into 5 different categories. And what we are going to do is we are going to talk about these 5 different categories today. So starting so far, I think you might have understood what is the data engineering and how it is critical for to enable data scientists to carry out their work basically. And what data engineers do, they basically set up the data infrastructure in the organization, those pipelines, data lake, data warehouse, from where data scientists can consume the data. So let's go into the challenges. So first one is the metadata management, that is data about data or metadata. So there are several pieces of information that are not readily available in data itself, and that a big data platform must provide. A lot of the organization, they don't maintain proper inventory, so they lose track of who are the data owners who are responsible for this particular data, and data is relying on the infrastructure for a long period of time. So firstly, there is simply the description of various data sets. So what are the various columns? What are the purpose of a table is? The metadata needs to be searchable, so making it easy for user to identify and find relevant data in the system. There is something we call it as data dictionary. So these are some of the common challenges faced in terms of metadata management. The next one is with respect to metadata management is data lineage. So where the data comes from, how it is sourced. This is critical for compliance implication, because there is a purpose for a data and it cannot be used for other purpose if that data is critical or it contains PI data, that is personal identifiable information. So why this is critical again, so that you can lock down or you can anonymize those sensitive data before anyone can consume those kind of data. So data layer consists of tables. The metadata layer normally consists of schema documenting the tables. So these are some of the common challenges which are faced during data engineering or implementation to handle metadata management. Second one is monitoring and auditing. This is one of the keys, because normally what happens in an organization, data scientists, they normally run their notebooks, Jupyter notebooks or via Zeppelin or various other AI notebooks on GCP through on their own project, on their own environment, and they consume data from another environment, say a data lake which is set up on another, or a data warehouse which is on another environment. So that is why it is critical to audit that data, who is accessing what and from where, and also for the monitoring purpose. So this is the key for the platform owners as part of the data engineering, who maintain that platform for which enables data scientists to consume that data and process that data and apply machine learning on top of it. So this is the kind of a second data engineering challenge which is broadly classified. Third one is data quality and validation. The quality of all analytics and machine learning outputs depend on the quality of underlying data. There are multiple aspects to data quality. So if you talk about data quality, there are 6 dimensions of data quality. Normally we call it completeness, consistency, conformity, accuracy, integrity, and availability. So these are the 6 key C's which needs to be met for data quality checks to be enabled. A lot of organizations implement their own framework, Spark-based framework, or if the cloud provider provides some cloud native service, they use that for the data quality checks and validation, whether the data is accurate, data is complete, data is available on time. So a reliable data platform can run various types of data quality tests on the managed data sets, both at scheduled times and during the ingress of the data as well. So this is where the challenge lies with the data engineering to get this implemented to make sure the data is of quality which is expected by the data scientist. So talking about data integration and data orchestration. So data integration means you need to integrate with multiple data systems. There is a vast majority of sources available. the cloud technology market is evolving rapidly, and it spans various sets of open source and commercial data technologies, tools, and products. So as part of data engineering, we need the capability to integrate with those systems, those source systems. There is no one size that fits all data fabric, basically. So because data platforms often needs to integrate data from multiple sources and provide data to multiple destination, we often don't get to decide. Teams that are upstream in the workflow expose data from solutions that make sense for their needs, while the teams which are downstream want data to be in their format, which are specific to their needs, their requirements, basically. So there is a need for an orchestration pipeline where you transform data based on different needs of different teams, basically. So that is where the challenge lies for data integration and data orchestration, making data available in different formats to different people as per their requirements. The last one is kind of data ops practices, basically implementing DevOps practices when you do data engineering. Another work area in bringing engineering to workflows supported by other disciplines such as data science and machine learning engineering. With a small team, it's relatively easy to create ad hoc reports and run ad hoc machine learning. But this approach doesn't scale, basically. So one production system depends on the output. This workflow must be reliable and should be scalable. That is why it is key to implement DevOps practices when doing the data engineering. Just to summarize again, what is the role? Data engineers are experts in designing, building, and maintaining database systems in support of an organization, analytical and transactional operations. Data engineer do most of the groundwork that supports data science workloads, basically. So this was all about the challenges. We have talked about data engineering. Let's look at the solution. What solution as part of Apps Broker we provide? So solution is to utilize modular, pluggable, flexible, and customizable accelerators, which address all of the data engineering challenges and incorporated all of the best practices and experience of delivering wide number of projects. So Apps Broker enable, so this all the accelerators, what you see is kind of at a high level, and underneath there are multiple pluggable, modular, customizable accelerators, or script we call it, which together combines it to make a data lake accelerator or MLOps accelerator or logging and monitoring accelerator or data warehouse accelerator, you can call it. So accelerator enables continuous and automated delivery of data to power BI analytics, data science products, basically. Also enables organization to build their own modern lakehouse and data mesh architecture, which is required for empowering technology and people. This accelerator integrates well together to provide a larger functionality set, or can also be used individually. It has been designed in a way that it allows modularity, flexibility, and extensibility. So that is where you see it. All of the small accelerator combines to make a big, large functionality. We call it MLOps accelerator normally. So data landscape is dynamic space, and in many situations, clients do not need a fully integrated end-to-end solution or end-to-end platform. Rather, enterprises are looking for small accelerators which solve their particular specific technical or business requirement to realize a data platform solution or to meet their business outcomes, basically. So this accelerators enables business to quickly deploy a centralized next generation platform to ingest, store, and process data, and also to migrate from their on-premise to their cloud environment. It significantly add values by enabling consistency and reuse around infrastructure, technology, pipelines, and processes. Being modular, flexible, they allow customization at runtime, enable easy tailor-made solution, jump-starting the data science team to create AI ML models, save time, effort, and consistency to standardization and reuse of data components and pipeline. So basically, our solution is AppsBroker Accelerator, through which we achieve through automation of various small accelerator, which incorporates all the best practices and our past experience. So this is the solution which we are recommending to solve all of the data engineering challenges and all of the machine learning challenges which we are facing in day-to-day lives as part of the organization. So moving on to the next slide, just wanted to show you how this accelerator helps in each of the stages. It helps right from data ingestion to data transformation to data enablement. So there are multiple challenges we have seen as part of data engineering at each and every stage. And there are a lot of scope for automation at each and every stages of this, pipeline. which will ultimately enable a data scientist to do some data innovation and visualize the result, and which will become a business outcome, and they will realize the value. So this accelerator helps in this data journey to quickly move to progress through these stages, ultimately reach the business goal basically. So yeah, so this is about the solution from my side. I will hand over to Santosh to talk about case study on MLOps accelerator and talk about the benefits now. Thank you.
Absolutely. Thank you, Manish. So if I may add just a point on that. So Manish has talked about how important the accelerators are. And the underlying point is not all enterprises will need all the accelerators all the time. So we need a solution which can quickly fit in to their ecosystem and do the job for us, and do the job in a reliable, sustainable, reproducible, reusable fashion. So we tick off all the good qualities of ML engineering, and we also tick off all the good qualities of the underlying data engineering aspects that we need to get the maximum benefit out of the smart analytics. That is what it is all about. So how quickly can we integrate our system into the existing ecosystem? That's the core. So we wanted to show you a quick overview of how one of those accelerators will look like. So far we have been using that word quite a lot, number of times. So what exactly is an accelerator in physical form? So that's what this is. So this is a piece of a version of MLOps accelerator. What we do is, you can see there are lot many GCP resources working here. They work in tandem with each other, doing their own job, but the overall output of this accelerator is an ideal MLOps solution. That's what it is. I'm not going to go through each and every component. I'm sure all of us are aware of the advantages of all these resources. So at a very high level, so I'll quote some examples. So Manish has called out a very interesting point where data scientists often work with quick experimentation. They're quite comfortable with notebooks. That's it. We need the notebooks. So we get in the notebooks into the system, and we make those notebooks reusable and reusable pipeline artifacts. That's what the accelerator does. Now we have a team, very mature team, coming up with a modular based programming for all the modeling, pre-processing, evaluation. Yes, that's fine. So we will use this accelerator to take that part of the input, and again apply that and get it out as a pipeline artifact. So we have got various connectors into the pipeline, where we take in the data, we take in the model inputs or programs or code configuration, and we produce something called as the pipeline artifacts, which are reusable and configurable. And for that we use various GCP resources and the built-in containers. And these containers are the publicly available containers, customized containers we created based on our own experience. So we augment whatever the data scientists or wider ML teams give us with those specifications, and we create those pipelines, and then we use the underlying architecture to train, execute, evaluate. So all the orchestration happens on the architecture. Again, there is a flexibility for the enterprises. Can we go for a Vertex AI completely serverless solution, or can we go for an existing in-house system, Kubeflow or Kubernetes engine with the all the custom mechanics to it? Or can we use Vertex AI experimentation, or can we go for ML flow? Most of the some of the organizations are uh, quite familiar with technologies such as ML flow for their tracking service, model staging service. Yes, that can be plugged into our accelerator. So overall, you see this as a plug and play kind of an architecture, which will help organizations experiment and adopt and get benefits out of the ML use cases. So one of the greater advantages is the quick proof of concept that we can put through this architecture. That's so it's very easy to get the system up and running, do an MVP, get the benefits, and then plan for productionization or a full product review. So and the other characteristics of the pipeline itself are, we have got number of connectors that can be connected to the pipeline, and all of this pipeline is agnostic to the type of framework which data scientists use. It can be a scikit-learn, XGBoost, Keras, it doesn't matter. The programming language itself, which is one of the key benefits for developers. So some of them are quite comfortable with Python, some are comfortable with Go for pre-processing or Java for pre-processing. That's an architectural uh, that's a preferred programming language for a specific team in an organization that can be supported. And same thing applies for various DevOps pipelines as well. So all of this can be it can be we can apply CI/CD concepts to this accelerator using cloud native solution, or these can be handled by existing enterprise CI/CD architecture. So what it essentially means is this is highly customizable. We can plug and play different services of this pipeline, and that depends on what exactly the enterprise wants, and how quickly can we do it. So yeah, so that this should hopefully give you what an accelerator is. The same thing applies for the data accelerator and other accelerators that Manish has talked about in a minute. Moving on to the next slide. So these are the key benefits that these are the tangible benefits that organizations can attain by leveraging all the data accelerators, MLOps accelerators. This is depending upon what depending upon the work we have done for the clients. So what it is so we will be reducing a massive benefit in time, in terms of time and effort, by reducing the discovery phase in any projects, and of course the delivery time, because these are think of them as a white label solutions within the system where you can adopt to your ecosystem. Customization is, of course, it has reduced, because all the customization is configurational driven, code driven. And as I said, so I think this is repeating myself a lot. So repeatability and reusability is at the core of this idea, and that makes ML deployment patterns very easy to experiment with and use. And agnostic, the entire pipeline itself is quite agnostic to any kind of a framework, programming language, systems we use, which ultimately which ultimately results in a good collaboration between different teams: data scientists, engineers, data engineers, sorry, DevOps engineers. So these are the key benefits that we get out of GCP. Yeah, that ends our presentation.
Thank you for listening to us. Yes, sir, I think our presentation is done now. You're on it.
Yeah, thank you, Santosh and Manish. Sorry, I was muted. So, would you put some light on, if we have multiple ML processes going on and we use the same data and make us some sort of pipeline in the system, so the data is reusable and a new model is being generated, tested, and then repeated. So the evolution process goes on with the new data comes in, and it so something like that we can do in this platform.
Yes.
Exactly, yes, sir. So sorry, Manish, do you want to go first?
No, I just wanted to say yes, that is possible. And what
Yeah.
you're talking about is kind of a CI/CD pipeline, which you will set up where you will go through different environments, train data, and that pipeline is reusable for various different data sets, data sources.
Yeah. So to expand on that, Yasser, so one of the use cases we are currently working on is as a time series prediction. We are creating models to predict future events based on the historic events. So what happens is the pipeline just not a single run. What happens is there is a feedback loop also built in, which takes care of all the new data that is coming into the system, retrains itself in the future, so it becomes intelligent as we go ahead in the future, getting more data training on doing the forecasts for the future.
All right. Thank you, Santosh. Thank you very much. We wait for the questions from the audience, but apparently there is no question yet. So we'll move towards our new host, Christopher. I'll put you in the background now.
Yeah.
Thank you very much, Santosh and Matil. Nice day.
Thank you.
So our next speaker is Christopher. He's basically working for Cisco, and he's from Amsterdam. He's going to talk about how to detect malware in encrypted traffic without decryption. Very nice topic. I'm bringing him in. So that's hi, Christopher.
Hey, how's it going?
Yeah, very interesting topic you have here today.
Thank you.
Tell us about yourself to the audience, and then we can move towards your presentation.
Okay, like an introduction, you mean?
Yeah.
Yeah, okay. Yeah, hi everyone. Christopher van der Made. I'm a developer advocate at Cisco Developers Program. And yeah, I focus specifically on security. So anything that has to do with cybersecurity and Cisco security products. And yeah, excited to be here today.
Yeah. Can you please share your presentation so we can start? Okay, over to you, Christopher. I'll be going into the background. So
Sounds good. Okay, so welcome everyone to my presentation on how to detect malware in encrypted traffic without decryption. I already introduced myself briefly, but just to go over it once more. Name is Christopher van der Made. I'm half Dutch, half American, living in the Netherlands, in Rotterdam now. Studied in Amsterdam, did a combination of neuroscience and computer science, then a master's in information science. I joined Cisco in 2015 as an associate systems engineer. Then I worked as a consultant engineer for security for a couple of years. And now, since the beginning of 2020, I'm a developer advocate focusing on security as well. So I've been doing cybersecurity for a couple of years now. And I'm yeah, very interested always in topics related to security, but also look at my background. I'm also yeah, very interested into computer science and machine learning and those kinds of things. So today's presentation will combine everything. My presentation will be around 20 or 25 minutes. If you have any questions, drop them in the chat or yeah, whatever works best. I also will have my contact details at the end, so you can also reach out to me privately, of course. So the agenda for today, first we'll go through how encryption works. So it's kind of like an encryption 101, but I think it's important for everyone to understand how it works and how the protocols are evolving and what kind of challenges that brings with it. Then we'll talk a bit about how you can actually decide in encrypted traffic what is benign and what is malicious. So what is good, what is bad traffic. So how can I dissect between a encrypted traffic flow from malware or an encrypted traffic flow from Google Chrome, which is totally okay. Then I'll open up the hood. So I'm going to talk about an open source project from Cisco. And yeah, basically everyone can access it and use it however they want. And I'll talk a little bit about the machine learning algorithms behind it. And yeah, the choices that were made during the project. And yeah, we'll finish up with some concluding remarks. So how does encryption work again? Now, before I dive into yeah, more of the details, Let's first have a look at a challenge that we have. So encryption, obviously, as people know, basically makes the information in a traffic flow, or if it's data at rest, makes it unreadable unless you have the key to unlock it. So that is basically a very basic explanation of what it does. You lock information or data either at rest or in motion. Today, I'll be talking about data in motion. So I'll be specifically talking about TLS, which is the encryption protocol, which is being used all around the web nowadays. And this is basically the next step based on SSL. So whenever you hear SSL, that's a very old protocol. Everyone uses TLS now. Now the usage is increasing like ginormously, of course. So almost all traffic on the internet now is encrypted, which is a good thing. So this isn't necessarily bad. It's even very good. For our privacy, at least, it's very good. Yeah, we don't want anyone eavesdropping on our traffic. Now, the downside of this is that more classic and more legacy security systems were usually traffic based, and they were looking inside of the payload of traffic. And since that payload is now encrypted, so only the metadata is available now, not the actual data, we cannot now make a decision whether traffic is malicious or not based on the data, based on the payload. Because the content is encrypted. So now that is one thing, and so there were solutions to this. So you can decrypt traffic and re-encrypt it, so-called man in the middle. However, applications nowadays also don't like that. Also, man in the middle is very intensive, so it costs a lot of resources to do this. And yeah, with more futuristic or protocols, it's sometimes not possible. Banking apps, for example, use all kinds of tricks to make man in the middle impossible, or at least whenever they detect it, they'll basically drop the entire session. So this is also not the solution. So we're going to talk about a solution later, but I just wanted to have the problem statement clear. So the problem is we are not able to view the data in motion anymore due to encryption. So that means we cannot see the difference between traffic. We cannot see the actual, so we can't see if someone's downloading malware or streaming a video. Obviously, we can do a lot of smart things, but if you look at it very basically. Okay. Now, let's dive into encryption a little bit. And yeah, again, I don't know what the background is from everyone, so I'm going to give you a quick 101, and it's always nice to refresh your encryption knowledge. So when you talk about encryption, the important thing is that both sides, A and B, Alice and Bob, they need a key. And they need this key to encrypt the information and decrypt the information. So there's multiple keys that need to be exchanged. Now, how do you do this without someone in the middle just looking, oh, they're using this key, I'll steal all of these keys, and I can just decrypt the information. Known key decryption is what that called. So how do you exchange keys in a untrusted medium called the internet? Now, this is where Diffie-Hellman comes in, the Diffie-Hellman key exchange, and others as well, but Diffie-Hellman is one of the most known. Basically, Alice and Bob decide on a base or a common paint in this example. Obviously, this is a numerical value in when you talk about encryption. And what they then do is they both choose a secret key, or in this case, a secret paint color. What they do is they mix their secret with their common paint, and this results into two other types of paint. They exchange this over public transport because the assumption here is that you cannot go back. So you can do two colors plus each other, but it's very difficult to find out what the two colors were if you only have like the mixed color. And this is the same with how the key exchange algorithms work. It is very expensive from a resource perspective to go and calculate this. And it can take, depending on the cipher suites, etc., can take years or hundreds or thousands of years to calculate this, making it virtually impossible. Now, the nice thing is if you do this, and after this, you add this mixed paint with the secrets again, you actually get a common secret. So when you look at it this way, it's actually quite simple how key exchange works. And the nice thing is if they have a common secret, they can start encrypting and decrypting with it. So this is, in theory, how that works. Now, if you look at TLS 1.0 to 1.2, you can see a client and a server, so Alice and Bob. And basically what happens is the client says, hey, hello, I want to start encrypting with you, exchanging information in an encrypted way. The server says also hello. Then the server sends the certificate information. Then the client will do a key exchange. And basically they go back and forth 2 round trip times, basically. And the client will verify the certificate, check crypto parameters, etc. Now, if you go to the newer version of TLS 1.3, you already see, if I go back and forth, that there's less arrows. So basically what happens is that in TLS 1.3, which is launched a couple of years ago, so it's quite prevalent already on the internet, the key share is done immediately. And because the key is shared immediately, the server can actually send it back and start encrypting straight away. So first of all, it's less round trip times to start encrypting, so it's faster. Also, TLS 1.3 supports more secure cipher suites. But the key thing here is, the most important thing here is that the certificate is now encrypted when it's sent back. And this this wasn't the case prior to TLS 1.3. Now, in the certificate from the server, there's some crucial information on who the server is. Right now, we do not have that information anymore in the middle. So if you look at this again, basically this process is just made more efficient. Now, the challenges with man-in-the-middle decryption is that the common name and the subject alternative name, which are in basically subject fields in the certificate. So basically the server says, hey, I am google.com or I am apple.com. That name is now encrypted. So all we can see in the middle is, hey, there's a public IP address sending encrypted data back. That is a problem because we can now only rely on the server name indication, and the SNI is something that is in the client hello. However, the SNI can be spoofed because if I'm the client, if I am, I can do whatever I want as an SNI and send it to the public IP address. Now you might ask yourself, why would you do that? So what if we send a fake server name indication in the client hello? Well, the thing is here that the request sent to website A, not allowed, but indicating that we're going to website B, which is allowed. So the thing in the middle, which, for example, a firewall, which would decide if something is allowed or not, or a web proxy, now doesn't know. Now, a reason could be that you browse to forbidden websites, maybe a gambling website or whatever. That's pretty boring. But what if a malware connects via command and control through a decrypting device? Now, this is a better reason. So this is quite a long intro into how encryption works and what problems and challenges are with it. But what I hope that you take away from this is that with TLS 1.3, we cannot basically see what the traffic is anymore. So we can't know for sure that the server it's going to is basically benign or malicious, if it's good or bad, because that certificate coming back from the server is now encrypted with TLS 1.3. The only thing we can rely on is an IP address and the SNI, but again, the SNI can be spoofed. All right, enough about this. Let's move on. So how do we now decide which encrypted traffic is benign and malicious? How do we do that? So how do we know what to block and what to allow? Basically, if you really drill down, if you're looking at it from a security perspective. Now, luckily, there's two gentlemen, which I want to give all the credits to, by the way, because we're talking about some research that they did. But Blake Anderson and David McGrew both have PhD, one in computer science, the other one in physics, and both work at Cisco, the one a bit longer than the other, as you can see. But they've written two very interesting research articles, and I have the research articles link at the end, so don't worry, don't have to Google this. But basically, their first article was about identifying encrypted malware traffic with contextual flow data. So what they did here was they used information like the DNS response and HTTP headers, and also they used something called the sequence of packet lengths and time, so how many packets are being sent, and all of this they modeled using machine learning to basically decide on what traffic is benign and malicious, what is good, what is bad. Now, more recently, they did a new research based on their previous research. So if you were to read one, I would definitely recommend reading the newer one, but the previous one is also very interesting. And here what they do is they use TLS fingerprints and destination context to decide on, hey, where is this traffic going to? So who's the server here? And obviously, is this good or bad? And they do this in a very interesting method. And I'm going to explain you exactly how their research worked and why it is so innovative in my opinion. And yeah, as I mentioned, it's an open source tool. It's called Project Mercury, and I have the link for that as well in the end. It's written in C and C++, and it's basically a system that continuously collects and fuses billions of real-world TLS sessions and host logs. So it basically combines those host logs with TLS sessions and fuses that data so that you have both information from the device, for example, a laptop or server, and combines that with the network traffic, which is, very interesting. So it models all of that. So the TLS fingerprint plus host processes, and also with destination features. And the goal of it is obviously to create a machine learning or a model that can predict whether traffic is malicious or bad and from what process it originates. And I'll go through how they do that and what kind of algorithms they use. Now the challenge is with TLS fingerprints. So a TLS fingerprint basically is a fingerprint that combines some information from the TLS session, as I explained in the beginning, what those TLS sessions are. And for example, S channel, which is the default Windows TLS library, there's hundreds of processes that have the exact same S channel because they use default parameters. For example, if you look here, this is the same S channel TLS fingerprint, so the exact same fingerprint, but it's used by a lot of different apps. So it's being used by Microsoft Office, Internet Explorer, Cisco WebEx, but also maybe if a malware author is smart, he chooses to use the default TLS settings because systems looking at the TLS fingerprint won't see this as something which is out of the ordinary because it's just using regular TLS information. And as we know, malware is now also using encryption. So it's not just your internet, Google Chrome and Internet Explorer, etc., but also malware running on systems knows, hey, I'm going to use encryption because I can go undetected in a lot of systems, unless, of course, you use smart solutions like I'm explaining today. So in a nutshell, happening is the fingerprints, TLS fingerprints created from the client hello is being combined with source IP and port information and destination context. So this is the input. And the output that we want out of this system is what process is it from, is it malware, and what OS is it using. So this is, in general, what the algorithm is that we want to build. Now, let's explain some of the magic. Basically, there are two knowledge bases which were used to create this system, the project Mercury. So to train it, basically, on the one hand, they used benign or safe traffic collected from Cisco AnyConnect network visibility module. So this is a VPN client, but it does a lot more. Maybe you have heard of it. But it has a lot more systems in it, and it can collect network data, but also it collects process data as well, and the host operating system. So basically, as you can see here, we have the networking information and the process information, and we fuse that data into a system, into a knowledge base. Now, this is for the safe traffic. For the malicious traffic, we're using data from Cisco ThreatGrid, which is the sandbox solution from Cisco to basically detect malware by executing files. But in the sandbox, it collects a lot more information like process information, network information, etc. So it's a bit different solution how the data was captured, but the same data was captured for both knowledge bases. The most common malware families that were found from these samples were TrollDash, Tofsy, Emotet, and Dark Comet. Now, in total, as you can see here, over 9,000 unique TLS fingerprint strings were found, and almost 40,000 unique process executables. So a lot of different applications, basically, including malware, and a lot of different TLS fingerprint strings were all fused into a database. So here you see the TLS sessions for the safe information and the TLS sessions for the malware, basically. And they were fused, as I mentioned. So the endpoint information, so the process information and OS information is fused with the network information. And a system was trained, basically, with this. So this is all quite cool so far. Now, what did they use to? So what did they use to predict the outcomes, basically? So they used the famous Bayes model, And maybe you've seen this picture before. The chance of A given B equals the chance of B given A times the chance of A divided by the chance of B. B. Now, this model describes the probability of an event based on prior knowledge of conditions that might be related to the event, so A and B. So this is exactly what we're going to do. However, they used the weighted naive version of the Bayes model. Now, they used the two knowledge bases, as I explained before, as training data. So this knowledge basis had both the process information, the OS information, the malware information, as well as the traffic information. So the TLS fingerprint and the DNS or the destination context. And they created a weighted model because if they gave the server name and IP address a stronger weight, this was better to predict the process name and the malware verdict. So that's what they did. And basically, they have two features, the fingerprint and the destination context. And this is used to classify the client process name, malware detection, operating system name. So basically what they did, if I go back to the Bayes model, the chance of the process, so that is the input to process, or that's not, no, the chance of the process given the fingerprint and destination information. So the fingerprint and destination information is known, and we want to predict the process. So basically, what app on a device is actually doing this network connection? Is this Google Chrome? Is this malware? Is this WebEx? Is this whatever? So that is, in the end, the goal. Now, they received very high outcomes, so like 99.999 how do you call that? Accuracy to actually predict this. Also with so they had a new knowledge base that they didn't use to train the model, but just to test it, and they achieved very high scores and accuracy out of it. So I hope that I didn't go too fast, but I only had 25 minutes, and I hope it was interesting to you. I have some final remarks for you. Network encryption is increasingly important, and it's increasingly prevalent. It is changing the way we ensure data security. Remember, we used to be able to look into the data and block or allow traffic based on that, but we are not able to do that anymore. And malware is using encryption as well. So encryption-aware monitoring without decryption is one of the solutions. This enables process identification, malware detection, and compliance assessment. Now, as I said, it's an open source project, but there is actually a production implementation already. So it is very efficient and scalable. So here you see the encrypted visibility engine in Cisco Firepower. And as you can see, it's actually being used. Right now it is in beta mode. And there's also some other production implementations of Project Mercury. Now you can find everything here. So Project Mercury, this is the GitHub repo. This is the article that explains all of the research behind Project Mercury. And this is their previous research article and their previous GitHub repo called Project Joy. But this is now legacy, so I would recommend looking at Project Mercury. So with that, here is some of my contact details. If you want to reach out to me via Twitter, LinkedIn, GitHub, or email, then please use one of these handles. And thank you very much for listening in. I hope you enjoyed it.
Thank you, Christopher. Just a question. When it's going to be embedded in the Cisco devices? Is it going to be, or is?
Yeah, that's a good question. So actually, I showed you this slide. So this is actually one of the implementations that they've done. So this is a firewall from Cisco called Cisco Secure Firewall, or Firepower, I should say. And here they actually implemented this engine. So what it uses the TLS fingerprint and the destination context, which the firewall both has. And it uses the machine learning engine that the team built, the open source project, to actually predict malware and predict the process name. So as you can see here, you can see Safari, this is Chromium, this is whatever. And so here you can also see the top TLS fingerprint discovered processes and whether or not there is malware. So right now this is still in beta, and yeah, they're looking at implementing it in other solutions as well. But this is in production right now. I think you're on mute, Yasser.
Oh, thank you very much. So, if anybody have any questions, you can ask in the comments, so we can ask Christopher while we have the chance. So we will discuss a little bit 1 or 2 minutes, and then we can close the go for coffee break. So,
Okay.
Christopher, so basically, you're not obviously decrypting the traffic, just making ML based models and put
Yes.
the data in them, and recording all the malware type websites, and whenever there is a request going on to that website or the IP, you detect it as a malware request. Can you
Yes,
share
correct. So,
links in the comments, or you can show the slides? You can take a snapshot.
yeah,
Here we
here
go.
is. It's not the easiest link. I'm not sure if I can post it in the. I'll post it in the chat as soon as I'm done. Or you can take a screenshot from here.
Yeah, sure.
But indeed, basically, they trained a model to teach it. These are network connections that are bad, and these are network connections that are good. If you boil it down, that's what they did. And they used the available information, so metadata, instead of decrypting it and looking at the actual data. So it's better for privacy as well.
We have another question. Could we
Okay.
also use the same model for unencrypted traffic?
Yes, you could. That's a great question, actually. You could do that. The thing is, with unencrypted traffic, you could also look at the payload, of course. So there are tricks to filter based on the payload, but it's a lot more efficient to do it based on metadata than to actually look at the payload. So it's better for performance to do it via this way than looking at the payload. That's a good question.
Any other questions from the audience? No more questions. Thank you very much, Christopher. We'll have
thank you.
have a discussion some other day about the encryption and the model. I'm also working on ML in my time. So thank you very much.
All right. Thank you, and have a great rest of the day.
Bye bye. Okay, we are going to have a coffee break now, and we will be back in a bit. The back time will be 12:30. Thank you very much for joining us, and see you back.
Hello. Um, just one moment. Hello, everyone. Welcome to the afternoon session of DevFest 2021. Our afternoon pre-lunch. Just had our coffee break. I'm happy to introduce our first speaker. Sharmista Chatterjee has been, or is a GDE for machine learning, and has been a frequent speaker with us. Definitely is senior things, and so it's great pleasure to have you here. I'll let you get started if you're good to go.
Yeah. Are you able to see my screen?
Good.
On your bio, it says you're in Singapore. Are you currently there? You are able to hear me and see my screen?
Just one moment.
What time is it?
Hello. Just give us a few moments. I think we have some technical difficulties.
Composing a new world.
Hello. I think I should be able to hear you now. That was totally on my side. I did not turn on my Bluetooth headphones, so I'm so sorry. I'll let you go ahead so people can see more than this absolute mess of a hosting. Okay. Do you have your slides ready?
Yeah, can you see my
So
slides?
what we do, Carlos?
Yes, yes. I'll add them there. Okay.
Okay, let's get
Good.
started. You can hear
Perfect.
me? Yeah, thank you.
All good. Talk to you at the end. Okay.
Yeah,
Good luck.
thank you.
Bye bye. Thank you for
Hi,
being here.
thanks. Hi, everyone. A very good afternoon. So, this is Sharmishta here. I'm a Google developer expert in machine learning and Google Cloud. And today we will cover Google's AI, ML, and cloud technologies, how they can help us to overcome some of the challenges in the healthcare industry. So, first of all, we will see why data democratization is needed in the healthcare industries. And then we will look into Google Technologies' role in data and AI ML democratization, explainability, and ethics, which are very important in the healthcare domain. Then case study. So, how is Google can help us, and what are things that we should keep in mind? And sustainable deployments for the healthcare industry. So let's look into the data democratization and healthcare industry from the perspective of the healthcare industry. So we see that there are providers on one side and players on other side. Whether it is, we have to think about a problem like we can have a 360-degree round-to-round setup between the patients, members, hospitals, nurses, IT providers, the research, the between one side the producers who are producing medicines, one side the doctors, and the other side of it like the patients. So from caregivers to clinicians to administrations, how do we have a data-driven approach in every aspect of it, not only in disease prediction, but how do we have the emergency services ready? How do we help patients to be hospitalized? How do we provide them with all the facilities? And how is the finance and the operations getting handled? So all this needs data and data processing models in real time. That decisions has to be taken and actions has to be taken. So what are the interoperable frameworks that Google is providing? Let's go through it, and we will also see some of the largest organizations like Moderna and who have adopted to the Google Cloud to solve their problems. So mainly what is needed is identification of key KPI metrics in healthcare domain. So how do you identify that you differentiate a disease between a non-disease, and evaluate the outcomes and have the workflow ready that you can have the proper validity and audits in the input data, as well as you are able to differentiate the diseases and produce a reasonable outcome which has a good amount of accuracy as well as privacy and other points of ethics. Now, how do we achieve that in considering that the data sources can be single or aggregated? So we have a data ingestion framework that we call about go through the GCP, and which allows like the native schema as well as formatting in raw data lake, and which most importantly has to be compliant with some of the security standards, that is HIPAA compliant, and all the services are managed through this framework. Like we can have processing in terms of petabytes and multi-layered security, and we have different sorts of API. We will see like the DCOM API, where we can create objects, we can have automated workflows for x-rays, different kind of medical imaging techniques, and and everything what we design in the workflow and the system using the leveraging the services are compliant, like all this security norms we have, like HL7, HIPAA, and all those standards are getting followed. And we have for the stream data processing, the data flow, the stream data processing, and we also can leverage the use of Vertex AI, which Google has launched recently. So one more as most important aspects in the healthcare industries is protect against privacy attacks. So I don't want my disease to get exposed to the external world. It has to be protected. So whether in point of machine learning, queries, storage, data has to be protected. And that's how the DLP service comes into play, that the cloud data loss prevention service, that all medical images or clinical and other types of data has to be incorporated or embedded within the DLP service. So it's very difficult for the attacker to get and retrieve the data and information. By attacker, I mean the people who are very much proficient in machine learning attacks. So, and the cloud security services, we have to have like binary authorization for deployment, trusted container images. So when we deploy the images, that also should not be susceptible to any kind of loss of confidential information. And when we have those deployments, we should do that in secured VPC service control, so that virtual security parameters are closely monitored and maintained, and they are not going outside, because this is very essential for sensitive data. So we also should use some of the services like cloud key management service, that is the KMS, and manage encryption key service to manage server side encryption. Other than that, from the hardware perspective also, we should be careful to use the hardware security models like HMS, so that customers can host their encryption keys and perform cryptographic operations. So from customer point of view, from data, from the hospital point of view, if they are storing some historic information of the customer diseases, as well as from the perspective of doctors and other providers who are using those services, it has to be ensured that a KMS service is built and used by everyone. And how do we do that in TensorFlow using the GCP? So TensorFlow, we all know that it is an enterprise level scalable cloud architecture, right? We can leverage everything to use it that. And when we have all those like as Google Cloud Security Compliance Program are there, so we have to go through all those compliance programs, that how do we integrate our services maintain into the Google Cloud, so that everything is automatically done. We don't have to do again a reading, or we have to do again a study that of whether my service is compliant to all the different needs that the healthcare industry demands. Okay, and then we have the how do we define the cloud environment. So we will see some of the tools and technologies that are exposed by Google, so that clinical data into are interoperable. It can be used by not only researchers, the hospitals, and the healthcare providers who are exposing the data, as well as the all the people who are circling the use of medical data, who are allowed or privileged to use those data, because we will talk about a concept of federated learning there, that everybody has all the security, knows the security norms, and are abide to that. Now we have some certain amount of Google Cloud services like BigQuery, where you can store the data, different ingest data from different sources, but is in a kind of SQL format. Then the data accounting, from where do you get the data, and the data lineage and the accounting, like where the data are getting ingested at where is the source, what is the time, expiry time. If you want to have the data permanently stored, we will move to some other cloud storage which is for infrequent access. Then we have the data silo directory, like maintenance of all the data records, and the governance, everything of this goes side by side, like the data and model governance, which input data have given rise to this type of model metric, and which data is doing a worse on the model performance results. So everything has to be maintained. So that's what Vertex AI comes in, which is able to do everything at once. Then we have the PubSub and the data flow, all these things which helps in the data ingestion and reading of the data from the necessary channels, or the necessary messaging services. And of course, the most important thing is the data DLP. So we are able to achieve all the speed, access, purpose, competitiveness, and agility using all this. And this just this most important thing is, I would say, the labeling task. So Google Cloud also in medical domain, what we see is all diseases are not that much available among all sectors of the population. Few diseases could be very much less presence in certain sectors of the population. So data labeling is one of the most important tasks in kind of medical research, right? So because a very rare kind of a cancer may be present among certain people, and that too may be very much sparsely distributed among different population sectors. So that needs human intervention, and that is, we call a term called active learning, which needs human intervention and doing labeling task. So getting the new kind of images from human body and knowing that what is the tendency of the disease. So that is what Google Cloud is providing, a human intervention to label the task. And then when we have labeled data, we can use some of the other services which you have talked about, BigQuery, this cloud spanner for scaling SQL queries, for much for the high level scalability. We have the spanner. Then we have the different models, and of course we should use automable. We will see that how for vision and automable can be combined together in the field of medical, so that we are able to detect different categories of images from different sources, and then we evaluate the model. And there are a whole lot of API services present, where we can just use the services and give the prediction, or we can use the services and create our, like, use a post request and create some sort of images and label, and say that this is kind of images have been gathered from this kind of hospitals, and store it following the DCOM format and the DCOM medical imaging format, or the standard and the compliance. So we have the raw data, we have the de-identification, and the reacted data for analytics. So as per GDPR and all the standards, we should not store like the exposed, like the direct medical images, or the direct PII related information, like this individual, this age, this sex has this kind of disease. Everything should be encrypted, and that could be done through that DLP service. Now that we have the Vertex AI platform that we should be leveraging in using the healthcare, providing any healthcare API service, like we offer any product monitoring for a human body. We are having sensors, the IoT devices, or the Internet of Medical devices, which are get connected to human body, and they send certain results, and that gets uploaded to the cloud. Now what will the cloud do, apart from, like, we all know that we train the data from concept of federated learning. Like many of the devices from individual human bodies may collect information, and they can give a prediction, or from a certain human body it gets trained, local training from the device, and gets aggregated at the server. So what are we going to do? For whom that Vertex AI can come most important apart from training? So somebody, say healthcare medical provider who is producing medicines, or who is trying to, from the researcher's point of perspective, who are analyzing different kinds of trends in a human body, say during COVID. So that time, this could be a very important use case of using the Vertex AI, because we can get the data from different types of human body, monitor them, have a federated model, but trying to understand what are the symptoms from different cases of COVID, right? And then have a feature store in it, like isolating different kinds of features. Somebody may show a different kind of a lung infection, somebody may show a different kind of a diarrhea. So how do we isolate the features for different types of symptoms for a particular disease? That you can use the features for feature store in Vertex AI. Of course, we can do hyperparameter tuning, and when we are rolling out medicines, say whether this medicine is effective or not, we can turn out A/B testing. So we recommend medicines, and we said that these medicines can be used by a particular group, and say turn out the medicine for, say, 90% of the population or 40% of the population, and don't grieve the medicine for the rest remaining population. A/B testing, that is also possible through Vertex AI. So we know that the impact of the medicine that is coming out through a workflow and like a cloud platform like Google. Here you can see that the AutoML for vision, like, so we combine the Google Cloud's AutoML Vision Edge technology to understand different kinds of pneumonia, whether it is a viral pneumonia, or is a bacterial pneumonia, or is a normal pneumonia. So showing the chest images shows, for the first one is a clear, while this second and the third, you see there is hazy, some kind of an abnormality is associated. Now how do we do that? So AutoML Vision Edge, it trains the models with high accuracy, and it can get data from different devices. Of course, we can even have a IoT device and get some images from the human body. And then with, as we talked about, like we have like the human leveling services, Google's human leveling services, which solves many cases of active learning. And this image can be used for a variety of diseases, and within the variety of diseases, isolating, see, pneumonia is ultimately, at the end of the day, it's a lung infection. But if you try to isolate for a lung infection, what could be the causes? Could be pneumonia, it could be some other kind of lung infection. So how do we analyze those different categories of images? That is how, where Vision API can be clubbed with AutoML. And then this is the workflow, like from cloud storage, it can be pushed into the, like PubSub, or to an app engine, and from the app engine calls the machine learning APIs to know, like to know that what are the keywords or for the identification of the images. What are the images that it is looking for? And then vision API detects the broad objects and the labels the detection, and so that it is searchable. So this is searchable across broad topics. And it also detects like custom labels, like which have been newly done through active learning, identifies those, categorizes those images, and sends it through the APIs that could be available in a user device. So that's having said that, these are the important things for auto vision and auto ML. We have to train the models, and if the models are out of a large scale, coming from a large scale data, then this is, we all know this. Some of you maybe in machine learning already know some of the Apache Airflow, Apache Bing, and Kubeflow pipelines. So this is an orchestration layer, nothing but so management of the pods when they are deployed. So how do the pods, even if sometimes something happens and the data center go down, it should be another data center should be managing it, or one pod goes down, there should be auto scaling options, so the other pods fawns up, and there is no downtime in the service, so that the TensorFlow serving will be serving those requests. And even if you update a model, so there should be no downtime, and TensorFlow serving will be taken care of, serving the models to the user. And we can have different kinds of feature analysis. What is the accuracy metrics? This is the same for any other machine learning model that serves, but we should be more doing it on a real-time basis, because in healthcare, if a small change in body metrics, like a metric for sugar or say any other heart signal, can create a devastating effect if we are not doing it on a real time and not making the patients aware of the situation and taking necessary actions. So key pointers, what we would see in AI ML democratization is climate changes and removing bias. For healthcare industry, what comes most important is like the disease prediction should be agnostic. There should be no bias corresponding to gender and ethnic groups. And as we talked about that, whether it is fair and privacy, which are the main pillars of healthcare industry, how reliable our results. We cannot fail to detect a disease, an important heart attack. We cannot help to detect it after 10 minutes. We have to be very immediate and use the real-time pipelines. And what is that? That is the dynamicity and decentralization. Instead of having everything on one place, how do we decentralize the systems? And sustainable deployment, we will see later. So when we talk about privacy, how do we incorporate privacy? So one thing Google provides is the differential privacy, TensorFlow privacy, which has been there with Google. And we use constraint type of model development techniques. We put a constraint in model development. So there are examples later. If you want, you can connect with me. And then you have the auto ML. So you get the data from BigQuery to the original database, do some analysis of the schema, feature engineering. You can see 2, 3. Then afterwards, you have a data mining with DP. When you fetch the results to the query, the SQL queries all should be differentially private queries, so that those mechanisms should be possible with using Google Cloud. And then also when you build, these are two important steps, like doing query analysis and to building models. They should be differentially private, and we use epsilon to a metric that denotes how much is my model is private, how much information, confidential information it is able to retain. It is not going exposing sensitive information to the external people or the external attackers, adversarial attacks. Now, another important thing for the healthcare is, are we able to explain the models? Here you see there are certain pixels which looks different, and the X-ray was not able to detect what has the disease be, because it is just a pen mark by the doctor. And that's why we have to be very careful that my model is able to differentiate such small things. It's not from the medical inside the patient's body that is coming, but it is ultimately a pen which has been marked by a doctor. So that's the feature attributions, and there are different types of deep learning techniques and which are coming up with different feature attributions, explainability from different hidden layers of the neurons. We have so many layers, so that needs to be so those libraries need to be plugged in. And when we talk about fairness, we have seen that we have the what if tool. I think most of you will be familiar with it, to better understand that whether my input data is also is biased, then my model will be biased. So we should be able to explain that even if my model has given unfair outcomes, that is due to the data, the proportional of data of healthcare data from the black people is already skewed. We don't have so much data for the black people, so there, of course, we will predict from the models that they are more susceptible to cancer. Because another thing, black people don't get proper healthcare services. In the COVID times, we have seen many cases which have been attributed to the minorities. Why it is? Do we have sufficient data, or do they don't have proper medical or healthcare facilities? Can we look at those data and explain that is the reason why here black is showing more than white? So everything should be explained. So let's look at a case study, like key features for a democratization. Like when even we trained like models in for image analysis, because the deep learning is very expensive, it needs huge computing resources. Like how do we make efficient predictions? So one of the things is we can use data from different sources, that is the federated learning. And federated learning, we must be aware, like we should explore better options, like when the small devices, the IoT, participate in the training process, because they are also power hungry. And then, so predicting a person how much he needs an emergency room, and what are the symptoms he's showing, does he need oxygen, all these things have been carried out using 20 hospitals across the world. And that is a special use case that can be deployed in Google Cloud using the GPUs. So there are certain cases we will see that the medical providers have been very happy with the Google Cloud, because using transfer learning including federated learning and including federated transfer learning, how different data collaboration facilities can be done in healthcare system. So this is another case of another explain where we use data aggregation from different models, and ultimately the model is trained from one perspective, one market, and that is exposed into the another, the API is served into the another market. And Google Cloud Healthcare Data Protective Toolkit, that is, you can use it as it is an automation framework for deploying Google Cloud resources to store healthcare data, right? So including protected healthcare information. So this may sound a little bit like, if you don't know how we will do that, but there are providers who have been doing this kind of transfer learning, federated transfer learning, that requires vast GPU with the Google. That is the case which is we know the more vaccine maker, the Moderna, has used, and they were very satisfied using the multi-cloud data strategy to use and integrate based tools. There have been internal and external data sets for complete view of the clinical trials, like the A/B testing we have talked about. The Vertex AI helps us increases diversity of trials, trying from different racial sections. That is the explainability, the fair what if tool. And then we have other than shipments, how do you distribute the vaccine and medicines? That is, of course, there. You can use different optimization algorithms. That the NLP, which is another important thing, to timely analyze structured data from different sources. So this is it would typically look like a healthcare API going through the Google Cloud data flow, then BigQuery and the data lab. Like the data lab will help you to explore all the different data features which is coming in from the ingestion pipeline. This is nothing but the ingestion pipeline where we can get data from healthcare API or PubSub or cloud storage. Then this kind of a Hadoop kind of a tool called Dataproc, which stores the data in BigQuery, which is left to you, and then you can analyze the data using data lab. And similarly, large volume of data ingestion with Google Healthcare API, if you want to do that. This is what I was talking about, the DCOM API that helps. This is one of the standards for medical imaging, X-ray analysis. So we can either store an object when we get from somewhere, or we use existing objects to analyze or match with the images which I'm looking for, and also detect anomalies. Large volume scanning, that is, can be done by the Google Cloud Platform. So radiological image extraction, another case, like how we integrate with there are different categories of diseases which we want to process. One could be radiology, one could be cardiology, and then that everything comes onto DCOM API, and then we ingest have the data processing pipeline as before with the data loss prevention API, and ultimately is to do an analytics like which sector of the population showing, what is the predictability, when is the disease increasing, why it is increasing, providing all the explainability features. So it's very easy for search and retrieval and extraction in combination with other clinical data. So that's the expedited drug discovery. So there has been some very interesting case studies, and people have used this. The Schroeder CEO has said, so the availability of GPUs of Google has how it has helped to provision so much GPUs. It was such a cost saving for them. So run physics-based simulations requiring about a 20 requiring huge number of GPU per training the per molecule on a per molecule basis. So these are some of the data sets you would like to take care. Like Google also provides some of the data sets for analysis and all. And there has been extensive manual on that. How do you take the data sets, import into BigQuery and all. And would like to say that even this is a very short section that we will say that bring in sustainability. In any deployment, Google provides now all the carbon emission features, less energy, zero net emissions, and carbon free energy. That's the goal of Google Cloud Platform to go by 2030. So while we are very much knowing this and doing for other deployments, why not healthcare? Because for federated learning, there could be huge devices which could be sending data. And we are doing deep learning, federated learning on the centralized server, or on the using transfer learning, is using different types of heavy deep learning models that expedites a lot of energy. So we should be careful to evaluate a net neutral option, doing all the where to pick the data center. So some of the metrics what we should do, look at the Google Cloud and see like which choose Finland or Frankfurt, choose Finland or London, choose Iowa or North Virginia, and choose Oregon, not LA. Yeah, the end of the day is pick a low carbon region, run batch jobs, and set organization policies. So that lower carbon regions, all the teams are picking up lower carbon regions. These are some of the metrics. It's there in Google, any of the help pages you want to check for Google. And again, this is another use case, the Clara Train SDK, which has used the Google Healthcare data engine, used AI-assisted annotation, NLP, entities, TensorFlow, and have been very much useful, which has been very much useful for solving many of the medical use cases. Concluding thoughts, yes, and we need, and not only Google, but Google has also partnered with Intel for specialized chipsets, which can be plugged into different devices, that the IoT devices or IoT devices we were talking about. And that's the thing, that is the IoT gateway, and Google Cloud interacts, and that has been able to solve different problems related to healthcare industry. Thank you. So some of the fairness samples are here. Like we have tried to predict different types of mental health conditions using constrained TensorFlow or privacy. Constraint optimization means nothing but having the optimizer, which could be an Adam optimizer, any optimizer, have a constraint like so many types of data types has to be there for different racial groups, ensuring that rate is maintained. Yeah, it's there in my GitHub. Yeah. Thank you. Questions?
Thanks very much for that, Sharmista. So I will have to ask you for your slides, and we'll share them with the viewers because they weren't showing up. Sorry about that, but it was a very interesting talk. You're so knowledgeable. I had a question. Do you if anybody has questions, please post them. We'll have a few minutes for them now. But how do you get into healthcare, or what took your interest in getting into the healthcare industry and applying
Yeah.
AI?
Yeah, so I'm not a healthcare specialist, by the way, but I got more into healthcare using Google's federated learning. So exploring different cases of federated learning, transfer learning, and federated transfer learning, I got to know much about the healthcare industry and what Google is doing and its platforms are doing for the healthcare vaccine makers or for the different healthcare providers.
Right. That's excellent. Um, I'd, I think we can make so much difference with technology if we, apply it and have kind of curious people like yourself about it. I read that in your bio that you do both research and applied technical work, and
Yeah,
so that's all great. Thank you very much. I'll
thank
just
you.
see if
Thank you. I'll share the slides to you. Yeah,
please do. Yeah. Okay. Thank you very much.
thank you. Bye bye.
Bye bye. Uh, mm, mm. So now I will introduce our second speaker for the session. Um, Vasudev, welcome. So Vasudev is a senior machine learning engineer working at Accenture AI. And in the past, he did work related to Google Cloud, deep learning, and cloud computing. And his research areas include predictive analytics, video analytics, and his work has been published in more than 10 journals. And recently, he filed a patent. He is also 6 times certified on the Google Cloud platform, and he's an active open source contributor and had been a mentor at GSOC 21 and delivered over 20 technical talks in the past. We're very happy to have you here as well today. I'm looking forward to your talk, and I'll let you kick off. Or how are you today? I guess I can't forget about the human aspect.
Yeah, I'm good. Thank you.
um, Nice. It's nice that you could join us. You could join us online. So we're here in person as well.
Yeah,
So it's quite overwhelming in person, I have to say. So,
yes.
but thank you for joining us online. And yeah, I'll let you kick off. That's okay. There.
Thank you. Thanks for
Thank
that
you.
introduction. Yep, thank you. So, yeah, coming back to our topic today. So, I'm going to actually talk about MLOps and its best practices. So till now, we are at a stage in MLOps wherein every company is being matured enough to actually come to the MLOps playground and actually implement end-to-end ML pipelines. So this was not the state way back in 2018 or 2019. So it was very early stages back then. I mean, there were certain companies which we can count on wherein they were implementing end-to-end MLOps in their production systems. But though our end-to-end systems were not fully automated as we do in the software development. So we have a pure DevOps role, which actually does the end-to-end automation. But probably in next couple of years, it would be mandated for every machine learning project to have an MLOps pipeline, right? So we'll look at what exactly is a differentiator when we follow the best practices of MLOps, and also we'll also see how exactly the Vertex pipeline play a role in it, and an end-to-end example of the GCP platform. So right now, like in a particular set of organization, in a large organization, probably we have very specific roles, like right from governance to data engineer to data scientist. There are multiple people involved in a particular machine learning project delivery team or the product development team, wherein each team or each role has a certain responsibilities to play. But the end of the day, they need to be very interconnected. Any gap between them or any communication between them, if it is lapsed, then the entire process or entire product or entire delivery would be go for a toss. So in that situation, the automation is a key, wherein everything is managed by a framework or a tool, or theoretically we would be processing an end-to-end pipeline, right? So at the early stages, like when like back in 2013 or 14, we generally do write a load data. I mean, we write a different files for each and every step, wherein we load the data first and then save it in a flat file like CSV or Excel file, and then again run models on top of it, and then evaluate it and store the model results. So this was a very individual process. I mean, each step was varied, right? And after that, we have evolved in a situation wherein we used Jupyter notebooks that to separate for each version. Right now, we are evolving to a point wherein we need to maintain versions, like we have a code versions in Git. So in the same way, we need to maintain the model versions and the data versions as well, like which data for which model, which version. So this end-to-end tracking needs to be there in place. Right? So we'll see how exactly it's evolving and what are the best practices which are actually provided by Google. Right? So again, the expectation of machine learning pipelines is so much and so that everything needs to be configured and automated. But however, in reality, it's a mess, right? Unless we automate it and tweak each and every part of it. So it's not like a straightforward CI/CD pipeline of a software lifecycle, right? So let's say if my model decays over the time, I need to capture the drift. I need to retrain the model to have a reliable results. I need to again look at the new data and train it again. So these are some of the maintenance things or monitoring things which I need to look at it as a machine learning engineer, right? So we also have exactly that piece taken care of. So according to some of the companies which practice MLOps as a I mean in the organization or in the projects. So this is the state of ML, wherein they see that the integration between the teams is still is coming on, and it would take some time. But however, we need to implement the MLOps as a practice and as a mandate for the project delivery or product development teams. So these are some of the basics where exactly MLOps sits. Like we have a data engineering team and we have a data science team and a core app engineering team. So app engineering team is the one whoever works with the endpoints of ML. Like, let's say I have an API or I have a batch data endpoint wherein the entire data can be sent to that endpoint, and then after that I can directly call that API and get the results. So whoever integrates this probably on the front end or any app or any user interface for that matter would be from the app engineering team. So in between both the teams, we have ML engineering team, right? So again, the process, how exactly the ML process works. These again the basic things which we actually need to understand. Wherein the first step is ML development. So all the experimentation done by the statisticians or data science for that matter, anyone who are developing the models, and also the training operationalization, wherein if we get the first version of model which is deployable, after that how exactly we take it to production and what are the steps needed, like data validation and model validation, I mean in an automated way. So although in experimentation phase we do model validation, but that wouldn't be suffice when we actually deploy the model. Right, and continuous training is something which is required as the next step. For example, if we have the data in place but we don't have enough, incoming requests all the time, and the model decays because it have been trained on a different data. So I mean, the data distribution only changes. If the data distribution entirely changes from the point in where we train the model to the model which we are currently using in production. So if that data distribution changes, the entire model results will be changed. So we also need to think about it. So I have certain slides which explain clearly. So let's say in that next step would be model deployment. So nowadays model deployment can be done right from local systems to the Kubernetes engine, or for that matter, any particular compute resource. But how well it is managed depends upon the framework or tool which we use and how we deploy. And prediction serving continuous monitoring, we'll see that in detail. So this is again the MLOps flow. Generally what we have, like at a very granular level, we have infrastructure which is a compute part. So be it any cloud platform or private cloud or any data center for that matter, and then security and privacy, and then we have source and artifact repositories. So those are something which we have, like in traditional CI/CD we have Jenkins and some other Nexus repositories where we store our artifacts. Like we'll also see what exactly in ML ops we have, right? And we have ML metadata and artifact repository, like we have containers registry. So we'll see what exactly in ML ops or CI/CD of ML wherein we fit in. So again, my entire slides would be focusing on the diagrams, and I would explain with that. However, I have certain slides with text. So here, like the first step wherein the ML team or the modeling team gets the data is from the data engineering team. So that's how it works in the organizations. So firstly, we have like a big data lake, like a large data lake of 10 TB or 20 TB. So in that data lake, let's assume the data lake is of any blob storage or any data lake for that matter. Then I need to write some Spark queries and get the data. And on that data, I can start, writing my models. So, and that entire prototyping model have again the problem definition, data selection, exploration. So this is the core modeling and model development part. So we'll not discuss that for now. We'll see how ML engineering part works, wherein I have version control in it. For example, for model version 1, I am using 10 to 15 features, and model 2, 15 to 20 features. 20 features as a whole, and for the model 3, I'm using 30 features. Just assume this is the case, wherein I need to able to track each and every model and what are the features it is using. So for this, we need to maintain metadata and we need to maintain the config at each level, right? So for this, like we have certain things called feature store and data version control, right? And at this point, let's say in ML development, whatever we see here, the end goal or the end point of this particular entire process is a particular version of a model, which is deployable and have been approved by the developers that this model works in production for a certain data distributions, right? Now, next step is how exactly we take this model and make it a production ready, right? So here we have, let's assume in the real life scenario, we have developed something on Jupyter Notebook, and at the end of the day, I get some weight files or TF-like files or any files for that matter, right? So at this point, I have those files, and now how do I take this to production? So that's how we will see in the next step, right? So next step is again the training operationalization. So the main part here is automating end-to-end, like without touching anything, it needs to trigger. And we'll also see what are the triggers or what might be the potential triggers in the upcoming slides, right? So we have version control, wherein whenever the new version comes in, again, if you are a pure software developer, like then we put a triggers like when it pushes to a master branch or a release branch or a developer branch, run the entire CI/CD pipeline, do a unit testing and everything. So I have an example wherein we discuss these things as well. So when the code config comes, so first thing is we do a build, and then we have the integration testing, wherein the end-to-end, right from the data updation to the model, the model which is developed on the Jupyter Notebook, that needs to be replicated here in a way that it can be automated end-to-end, right? And then we have deployed to staging environment and acceptance testing. So we have certain KPIs for each model. Let's say my accuracy needs to be more than certain number or certain percentage, or any other KPIs for that matter. If for example, I am deploying a deep learning object detection model, then what is the efficiency of that model? So not only accuracy, but we have certain standard metrics and certain business problem related metrics which we need to look at. So that is the acceptance testing, and then deploy to production. So then in the production deployment, we do smoke test and then release. So all the pipeline components like software artifacts. So whatever in this pipeline, we write the config files and we write other files which are related to the pipeline would be saved in a registry. We'll also see what that registry is, right? And then we have a training pipeline end-to-end. So here the training pipeline can be of any framework, right? From Kubeflow pipelines or TFX framework or MLflow, any framework for that matter. So whatever we are discussing here now is the basis of everything. On top of it, we can use anything and implement this end-to-end. Okay. So this is just the steps which I have just said. and then the continuous training part. So at this point, what we had a model, let's say the model code, which would give the output as the weight files or TF-lite file. And now we have plugged in that code in an end-to-end pipeline, CI/CD pipeline, and in that, the next step is continuous training. We want to automate it. So what exactly we need for that? So we need a data set and feature repository. So why exactly we need that? So whenever the model trains, we want to retrieve the hyperparameters and train that model using the appropriate hyperparameters. And we also want all the evaluations performed by the pipeline. Let's say in that pipeline, the validation set and the training set distribution percentage and also the accuracy at the end. These needs to be saved or persisted in some metadata storage. So for that we have metadata. And next is retrieve. We need to retrieve the processed snapshots, right? So whenever we actually train the model, we need to be in a position to retrieve the entire artifacts. And then we have model registry and model training. So let's say if I want to have a certain summaries of descriptive like analysis or statistics or feature distributions over my entire model training, I need to be in a position, right, to show that. So it's nothing but the fancy term for that is explainable AI, wherein I need to show the feature importance and every other aspect of it, right? So how exactly continuous training works? So whatever we have seen right now. So this is the training operationalization pipeline. For that we have we will submit the data sets, like whatever the data on which my new model version needs to be trained, and a trigger. So these triggers, we will see the potential triggers. So data ingestion and then the data validation, like whatever the data transformations which we need, this can be again written in native Python, pandas or PySpark or Scala for that matter, anything. And then model training and tuning, model evaluation, and so these are the standard steps as we know. So what are the extra steps here? So data processing engine. Let's say I write my entire data transformations in PySpark, right, for example. So I need to have a cluster which supports PySpark distributed processing. So let's assume this is the cluster. And model training engine. Let's say if I want to train my model parallelly on GPU or TPU. So I need to have that infrastructure in place, which actually provided by Google Cloud or any other public cloud or a custom setup data center. And model evaluation engine. So this is the infrastructure. So what we do generally is from this pipeline, we would connect to the endpoints of the infrastructure on which our model need to be executed. So the endpoint again here is training model, which would be saved in model registry. Assume we have a kind of a Docker registry, we have a model registry. And in this pipeline, like for every run, it would generate a model and it would generate certain parameters or some stats which we need to save. So that would be saved in ML metadata and artifact repository. So at this point, what we have, so we have been evolved from a place wherein we have the model code and then plugged into the training operationalization pipeline. And from there, we have moved a step ahead wherein we have the continuous training pipeline. So next is deployment. So the deployment, how exactly it works? So the deployment has many parts for it. For example, deployment on the public cloud. If we go with Google Cloud itself, we have Vertex endpoints wherein we deploy our model there. And let's say at this point, we have a model saved in a trained model saved in the registry. Right? The next step is to send that model. Let's say if this model is approved, then we build and test and deploy. So again, at this point, online experimentation. So we have two models, candidate model and production model. So ideally, we do this testing part wherein whenever the model is pushed to the production, certain production data is sent to the candidate model and cross-check the results and then push that candidate model to the production model. Like all the results, whichever are predicted, will be again saved to the ML metadata. Now we are in a state wherein our model is pushed and our model is serving the live traffic on the public cloud. Let's say the model is deployed. So at this point we have prediction survey. Right? The model is deployed, and now how exactly we can serve? We have multiple ways. like online inference, batch inference, and streaming inference, embedded inference. So these are basically the mediums on which we can access our model results. Like we just send the data over the API payload, we get the data. That's the online inference. And streaming inference, embedded inference is nothing but, let's say, if I have my model deployed onto the device, for that matter, like mobile device or IoT device or any device, I get the inference on the fly, then it's an embedded inference. Like I get the results and I get the predictions. So those logs needs to be pulled into serving logs and then model monitoring engine. So in Google Cloud, the model monitoring engine is cloud operation service on which we can write custom queries and then do an end-to-end monitoring. If that is not used, then we have ELK stack wherein we push the entire logs to Elasticsearch and build dashboards on top of it to monitor each and every prediction, right? And then we have serving data and predictions and explanation. So this model consumer is nothing but the user. And then, this is nothing but the same thing which we have seen earlier. And continuous monitoring. So why exactly we need continuous monitoring? So at this point, we have deployed the model. So we have started from developing the model to serving the model with the inferences. Now we are in a point wherein we need continuous monitoring, right? So continuous monitoring is nothing but once we get the results, our monitoring engine needs to be in a position to monitor all the predictions and generate the deviations and generate day-by-day reports. Let's say if on day one I have served 500 to 1,000 requests, right? The entire report needs to be sent to certain stakeholders so that they evaluate the model performance, right? So these efficiency and effectiveness of the model would be actually taken care by the continuous monitoring. Right? So we'll see how exactly it works. So at this point, we have the serving logs. In serving logs, using the model monitoring module, so we write certain scripts wherein we get data drift detection and concept drift. So the data drift is nothing but how the data distribution is changing right from the model training to the expected data, which is coming for the inference. And we have continuous evaluation. So wherein this evaluates how the model performance is it decaying over the time or not. So then we have reference schemas, baseline schemas. We'll see how exactly these are also managed. Right? So next comes the continuous monitoring, wherein whenever the accuracy of the entire model is reducing over the time, like we need to actually look at retraining the model, or we need to at least consider the fact that the model performance is going down over the time. So we need to be in a position that the model needs to be retrained for sure. And that aspect is something which is thrown in the form of alerts or reports, day-by-day reports. Right? So now, at the end, we have data and model management. So we have evolved from model development to model monitoring. And in these entire steps, we have multiple things needs to be managed, right from hyperparameters or the features which we select, or the ML metadata, logs, and code itself, and the Docker images, or the model weight files, or any artifacts for that matter. How exactly these things are managed? So let's see how they are managed, right? So we have hyperparameters which are saved in the form of metadata. Like we can use any DB for that matter, generally NoSQL DBs. So I mean, on Google Cloud we use Cloud Firestore as a service, and in Vertex AI itself, in Vertex AI platform itself, we have feature store wherein we can save all these schemas and logs and evaluation metrics. So these are required, let's say, in the long run, wherein I am at the development phase and my model version is 100. And I want to look at my third or fourth model version or 50th model version or 52nd. So in that case, the main aspect is to look back and then reevaluate and then develop 101 version, right? So these things needs to be taken care of. Actually, when we automate this, entire pipeline works by saving this data here, right? And then comes stages of CI/CD. So in the first development experiment stage, we have output as source code. And when we build the pipeline integration, we have packages. And from package, we do a continuous delivery, we have a pipeline. And in continuous training, whenever the new data comes, we have trained model. and that trained model is deployed for prediction, and after prediction we have monitoring. So these are the stages in CI/CD pipeline, or the stages how we deploy a machine learning model. So whatever we have discussed till now, without that we can deploy the model, but that's something which is not a best practice. We need to have a distributed way of maintaining the each component of the end-to-end pipeline, right? So what might be the triggers, like on demand? Let's say this is a manual process wherein whenever I want to release a model, I want to retrain a model, I can do this on a schedule, right? Let's say fortnightly, I want to run the model. I can keep a schedule. Like for scheduler, we have certain like use orchestration engine or cloud scheduler service as well. And let's say on availability of new training data. So this is something which is event based. Whenever the certain event comes, we can write a pipeline and we can write a business logic wherein it would be triggered. And whatever we deploy on Vertex AI has a REST endpoint. From that, we can actually deploy, run the Vertex pipeline. Yeah. So on model performance degradation, so this is over the time. So we can set certain threshold. If that KPI is not met, it needs to retrain the model. So that is also possible. So then we come to the Google Cloud Platform, like how exactly this entire thing works or integrated with each other. So we have cloud source repositories, which manages the entire code. We have cloud build, which actually runs the test, Docker images and update component specs and compile Kubeflow pipeline. So these are the cloud build actions. And then we have container registry, which is an artifact repository. And then we have cloud storage, which is for the pipeline artifacts, right? And release gateway. Once this end-to-end thing happens, it releases the new version with the certain configurations. No? A Kubeflow pipeline runs. So what exactly Kubeflow pipeline does? So right from data extraction to validation, transformation, training. So this is again the same traditional way of developing an end-to-end model. So this data can be fetched from BigQuery, storage, platform training, and any other platform for that matter, any other service or product offering for that matter. So the developers directly can use data science environment to push the code to the repositories, and everything would be triggered automatically. So this is one way to look at it. And let's say these are the build steps. Like I'll clone the repo first and run unit test and add image, that means the Docker image, and then update the images and compile pipeline. With the updated model, I want to run the end-to-end pipeline and pipeline to these years, as we have seen. Right? So in in today's world, like everything is Dockerized, right? From as the microservices evolved and Kubernetes came into picture, like everything is containerized. So our models are also containerized for an efficient management. And so this picture just depicts the containerization of models, and models can be shipped directly. So in general, Kubeflow pipelines look like this. Like we can prepare the data and then train an NLU model or model evaluate. So these are some steps which we have. So in the short of time, we may not discuss the end-to-end, but I'll come to the Vertex pipeline. So this is how the Vertex pipeline looks, wherein I can create each task or each task for each particular step, and then moving forward, I can do a monitoring with the Vertex AI monitoring service as well. So I'm concluding my session here. So if you have any questions, you can drop in them in the chat. So mostly I have taken all my references from this white paper. So this is a good read, wherein if you want to explore more or in depth about the MLOps best practices, this is again written by the Google engineers. Right? So if you want to get in touch to me with me, so you can directly go into this link and drop in an email or a text, right? And that's it from my end. So if you have any questions, they are welcome.
Hi, Vasudev. Thank you very much for that. Thank you very much for that session. I'm trying to keep up with it, but it's a really handy one to be able to look over and try and implement. So you talk about Vertex AI, but I have a question. Did you have any is there any other tools that you would use, or your kind of favorite tools for MLOps? Is there anything else that you're gonna?
Yes, again, Vertex AI is a Google Cloud offering. So in the same way, for AWS, we have SageMaker, and for the native or open source tools, we have Kubeflow, MLflow. So every other service has some pros and cons, but however, they serve the same purpose.
Little bit, yeah.
Okay. Thank you. There's also a question here from Darun. Usually, online experimentation part will be conducted when the model is in staging environment, right?
Yeah.
Or it would be done in
High-level
production
thing.
environment. I don't know.
So the model experimentation part, again, done by the development phase to the staging phase. Once the entire experimentation is done and all the KPIs are met, then only it's released to the production.
Yeah.
But however, we have monitoring in place, which also automatically monitor those models.
Monitoring is very
And indirectly, it's the experimentation in production as well. But however, we stop it.
Very unfortunate. Nobody told us. Yeah.
Okay. Thank you very much.
So there is a
Then
phrase
if there's no other questions,
social
I'll
media,
let you
it's a
go.
trap.
Thank you very much for joining us today, and for an enlightening
Nobody
session
told
as
us.
well.
They put us in coding and
Bye.
they know you are not human, normal human.
Oh, and we have lunch break now, so we'll see you back again afterwards.
Enjoy your life. Don't know much. Knowledge is a
Thank
curse.
you.